Welcome to the channel. Let's move on to the next numerical. A three-phase 5 MVA 6.6 kV alternator with a reactance of 8%, which is connected to a feeder of series impedance of 0.12 plus J.048 ohm per phase per kilometer. So here it is in terms of ohms per phase per kilometer, and there is a transformer which is rated of 3 MVA 6.6 kV bar 33 kV, and there is a reactance of 5%. We have to determine the fault current which is supplied by the generator operating under no load with a voltage of 6.9 kV. Okay, so this changes you need to be very careful because it is working at 6.6, but there is a change voltage of 6.9 kV. So there is a fault of three phase which is going to occur at 15 km along the feeder. So this is not an 1.5, this is supposed to be a 15 kV. Okay, then this is a single line diagram we have. So first and primary most thing we have to calculate is we have to consider the base value. So you have to remember here that in this chapter we have to consider highest MVA rating. That's why what is the MVA base of the generator and the transformer. So generator is 5 MVA and transformer is of 3 MVA. Okay, we'll go for generator, and there is a voltage of 6.6 kV. Okay, so what is the voltage on the generator side is 6.6 kV. Okay, then we have to calculate what is the voltage on the transmission line side. Okay, the transformer rating is of 6.6 and 33, so this is also 6.6, okay, and 33. Okay, so we know that what is the voltage on the high voltage transmission line is equal to low voltage of the transformer in low voltage of the base. Okay, this is 6.6 into high voltage rating of the transformer divided by low voltage rating of the transformer. So 6.6 33 divided by 6.6 will get 33. Okay, so new value is also will become the 33. Okay, the 33 kV on the transmission line side. So these are the new values. Okay, this is new value, this is word value. Okay, next we have to draw a reactance diagram. So before that we have to calculate what is the reactance to generator, transformer and the transmission line. Okay, so reactance to generator, we have the formula that XPU new is equal to XPU volt into kV, sorry, MVA base new by volt into kV base square, volt by new square. So here we are not going with it because what is the voltage, okay, and the MVA rating. This is also 5 MVA and new MVA is also 5 MVA. What is the voltage? Volt value and new values are the same. So everything is going to be cancelled with each other. So you'll get 8% directly. So hence it is J.08 per it. Okay. Or else if you want you can write the equation and go for it. Okay. Then next coming to the transformer. Okay. The formula we know that. Okay. XP new volt is equal to XT old it MVA base new by old, okay, MVA base value kV base forward by kV base square new value. Okay, what is the reactance of the transformer is a 5%, so hence 0.05. MVA base new value is 5 MVA because is given. Okay, for the old value of the transformer it is 3 MVA. Okay, this is 3 MVA. And coming to that, what is the voltage on the transmission line? We are considering this is the old value, this is the new value. Okay, 33 by 33 square, hence it is 0.833 per unit will get. Okay, coming to that, the feeder, okay, or the transmission line, what we have. So this is the equation is important. It is not same as the generator and the transformer. ZTL transmission line per unit is equal to ZTL in ohm MVA base, okay, divided by kV base square. So what is the impedance of the transmission line? It is given 0.12 plus J.48, okay, J.48 multiplied by 15. Why it is 15? Because it is 15 kilometer length, okay. What is the MVA? Is 5 MVA. What is the voltage on the feeder? You have to see here, this is 33. 33 square of this value will get 0.0083 plus J.033 per unit. Then we have to draw the pre-fault impedance diagram. This is subjected to the generator, reactance, what we got, okay. And for this is a transformer, this is the value, and the feeder. There is a fault at this point, okay. And this is the VPF we have to calculate. So you have to notice here one thing, okay. What is that? So in the previous problem, if there is a fault at this point, okay, they were supposed to give there is a change in the voltage across this point, okay. I will give you example that. So if this is working at 33, if there is an voltage which is going to change as, okay, then there is a change, the voltage will become, it may be greater than 33 or less than that, okay. Let's give you example that consider a 35 or 36. But you have to see to that here in this problem, he has not given that there is a change in the terminal voltage across the fault. In place of the feeder, there is a change the voltage across the generator. What was the change the voltage across generator? Is 6.9 kV. Okay, this is something is different. Okay, this is 6.9 kV. Don't make it confusion between these things. Okay, so this is something different. This is 6.9 kV. So what you have to do? We have to convert this, the actual value and the base value. We'll get the per unit value. Transfer this into the feeder side. Okay, means we'll get in terms of the per unit value. Transfer this per unit value to the secondary side of the transformer or the feeder. Multiply with respect to that per unit value to the what is the voltage we have. So we'll get actual value of the fault. Because we have to calculate VPF. Where is a VPF actually? There is a fault at the feeder point. So this is quite difference. Okay. Then from this we can able to calculate what is ZTH. There is no problem with go with the ZTH because this generator, transformer and the feeder, everything is connected in series. By making this voltage source is short circuited. Okay, ZTH. By adding up all things we will get 0.0083 plus 0.04933. So what is the steps I explained? Okay, you can see here we have to find EG and the VPF. Okay, so I told you no, actual value is given, it is 6.9. We have to calculate in terms of per unit, actual value by base value. Actual value is 6.9, the base value is 6.6. How you got this? At the initial, while selecting the base value, this is subjected to generator, you have to keep it in mind. Okay, so I'll get 1.045 per unit. Okay, so we know that the per unit can be applied to the either primary and the secondary side of the transformer. Is it? So same concept which you are going to consider, that the pre-fault voltage at the fault point is the voltage under no load. How I got this 34.5? Okay, so this is nothing but what is the voltage on the distribution side? That's nothing, feeder is 33. Multiply with respect to this is the per unit value 1.0455. So this is 34.5 kV. This is what we got. Okay, so this is the value of 34.5. How do you got this value? Okay, this is something different. Okay, then we know that the formula VPF to calculate that actual value by base value. Actual value is how much? How you got this? Because multiplying this 1.045. 34.5. The base value on the feeder side is 33. So you'll get 1.045. You can see here, this is the equation, okay, this one and this one. So this is subjected to primary side, this is referred to secondary side. So from this we can once again prove that the per unit can be applied for the either side of the transformer of it. Okay, then to calculate fault current, so what is that VTH? Because with the help of the VPF we got it is 1.045 times 0. Okay, so we know that by using Thevenin circuit we can write there is a source and the impedance. How we go, what is this value? This is nothing but this is ZTH. Okay, this is Z Thevenin's equivalent. Okay, equivalent of ZTH. Okay, so this is the source of voltage and ZTH we have to calculate IF. Okay, IF. Okay, IF is equal to V by Z. So we know that V value 1.045 and ZTH also we know that you will get 5.33 at an angle of minus 87.5. So this is in terms of per unit. We have to calculate the base current. So where we are calculating, where is the fault? There is a fault across the feeder. Okay, MEA base current is KVA base divided by root of the KV value. Okay, so what is that? So we'll get, so MVA is 5 MVA anyhow divided by root 3 into what is the voltage in the feeder, because we are calculating the value of the fault current across the feeder. Okay, what is the voltage in the feeder is 33. Okay, base value 33 into 10 to the power of 3, so we'll get 466.25 at an angle of minus 87.5 degree amperes. So you have to be very careful here that do not make any unnecessary calculation. So be particular to that what he asked, that value you have to calculate and execute in the examination. Okay, let's discuss the next concept is concept of short circuit capacity of the bus. Let's consider that there is a 3 bus system, 1, 2 and the 3. Let's assume that there is a symmetrical fault which is going to take place on the bus 1. So when there is a fault on the bus 1, the voltage of the bus which is considered as 1 per unit. Whenever there is a fault which is going to take place, the voltage of the bus which is going to reduce almost to 0. At the same time, the voltage of the other buses will sag during the short circuit of the network. So normally we are interested in knowing the strength of the severity of the short circuit stress. So both these objectives are met by considering that the short circuit capacity or the fault level of the bus. Higher the short circuit capacity on the any other bus, so hence an infinite bus bar has infinite short circuit capacity and will remain in its magnitude of the pre-fault voltage and the post-fault current. So what does this mean that, so if you considering that the infinite bus, it can able to transfer so any magnitude of the voltage and the any magnitude of the current we can able to trap from the infinite bus. So if the fault current is measured in amperes and the system voltage in terms of volts, then there is a 3-phase system. Hence the short circuit MVA can be expressed as MVA short circuit is equal to root 3 times of VPF into IF into 10 to the power minus 6. So VPF is nothing but the pre-fault voltage which is measured in line to line. It is in terms of the volts. IF is nothing but the post-fault current in amperes in that magnitude of the bus. Let's consider this is the equation 1. We can write this equation 1. Okay. So by considering that as a normal system voltage, so again redrawing that MVA short circuit will become root 3. So VPF generally consider that this is the base value. Okay, into IF into 10 to the power minus 6. Call this equation as 2. And also we know that the fault current is calculated, okay, IF is equal to V by Z. So this is a three phase, that's why it is VB divided by root 3 in terms of amperes. Call this equation as 3. So substitute this equation 3 in the 2, that is nothing but IF, okay, in the equation 2, that is IF is equal to VB by root 3, okay, divided by Z. Okay, by substituting this we will get, okay, VB square divided by Z into minus 6. So this is nothing but we can write it as KV base square divided by Z. Okay, call this equation as the 4. Okay, then also we have that we know Z per unit can be written as Z in ohm into MA base divided by KV base square. Okay, so this is called, this equation is 5. So from the equation 4 and the 5, by using these two, we can calculate and write it as, so MVA short circuit is equal to MVA base divided by Z per unit. So this is noted that MVA base is the total 3-phase MVA and KV base is the line to line voltage. So it means that the circuit breaker what we are considering, it should be capable to withstand the pre-fault voltage and the post-fault current. So hence it is an logic to rate the breaker in terms of these two quantities, means that the short circuit capacity which is account for both, okay, voltage means the pre-fault voltage and the post value of the current rather than the short circuit current. So this equation is very important. So we are going to use it for many calculations to calculate the value of the short circuit. This is the another kind of the numerical. We have two generating stations which is supply a feeder through a bus which is shown in the figure. Okay, this is generator G1 and the generator G2, and there is additional power which is fed to the bus through a transformer from a large system. Okay, with the help of T2 we can consider that there is an infinite bus which is connected at this point. Okay, so there is a reactor which is X which is included between the transformer and the bus. Okay, transformer, this is transformer and the bus, to limit the short circuit rupturing capacity of the feeder circuit breaker B. Okay, this is the B, short circuit breaker B, to 333.3 MVA. Okay, so find the inductive reactance of the reactor which is required. Okay, we have to calculate the X value. The system data are given like this. Okay, G1 is 25 MVA, 15% reactance, G2 50 MVA, 20% reactance, transformer 100, okay, 8% reactance, T2 40 MVA, 10% reactance. So he has given that, assume that all the reactances are given on appropriate voltage basis. Choose a base of 100 MVA. So that's all this. He has given that we have to consider on the base of 100 MVA. And we have to note down here, he has not given what is the value of the voltage across the generator, generator 2 and the transformer, whatever the thing. So the equation will remains the same, but we are not going to consider the voltages. So what will happen? Okay, let's solve this. Given based on this, we have to consider MVA base is 100 MVA. So here there is no question of considering the base voltage because it is not subjected to the consider of the voltage. Okay, so we have to calculate G1, G2, transformer T1 and the T2. Okay, let's calculate one by one. So we know that XP new is equal to XPU new is equal to XPU volt into MA base new value divided by volt. Okay, MA base volt value. So there is no question of the voltage, so we are neglecting that voltage part. Okay, so considering that generator G1, it is a 15% reactance, okay, with this. So we can write it as 0.15. MEA base is 100, okay, volt value is 25, okay, you can see here, you can see to that 25 MEA. Similarly for the generator G2, okay, this is 20% reactance which is given here, okay, MEA base new is 100. This is the same for the entire system, okay. What is the volt value? Okay, 50. So similarly for the transformer T1, so for the transformer T2, okay, it is 0.08 because it is 8% is 100 by 100, okay. So you'll get 0.08 transformer T2, okay, transformer T2. So it is a 10% is 0.1, 100 by 140, you will get a 0.25, okay. Okay, sorry, there is a mistake here. It is not supposed to be 140. This is only 40, okay. This is not 140, okay. This is 40, okay. We will get a 0.25 per unit. So we have to draw the reactance diagram. So this is subject to generator 1 and the 2. This is the reactance which is required. This is the infinite bus, what means the transformer T2 which is connected through with the help of infinite bus. This is a transformer T1 and there is a fault. So we can wonder that why it is there is a source of EMF, because we are considering that the infinite bus system which is connected to this system means across this bus. So we are considering that, okay. Then so this generator G1 and G2 are connected in parallel, okay, means this, okay, this and this are connected in parallel, okay, parallel, and this is connected in series, okay. Whatever the values we have parallel, okay, again which is going to connect in parallel to the X and 0.25. So this and this are connected in parallel, you will get the value. These two are connected in series. Whatever the effective value which is coming in parallel, again it is going to connected in parallel to this network because there is a source of EMF at this point, okay. We'll get there is a single line and the value of the 0.08 is connected in series, okay. Let's see that I have written a sentence here, just you can go through that. So this 0.24 we got that it is 0.6 and 0.4 are connected in parallel, so you'll get this. So X plus 0.25, this is connected in series, okay. Again this value and this value are connected in parallel, okay, means you can see here 0.24 and X 0.25. So this is value is connected in parallel and which is in series with the 0.08, okay, in series with the 0.08. So after doing the simplification, we will get the equation 0.2x, 0.32x plus 0.0992 divided by x plus 0.049. All this equation is 1. We know that the equation MEA short circuit is equal to MEA base divided by Z per unit. So MEA base is 100. What we got? Z per unit values. This is the equation. Okay. This is denominator. This term is go to numerator. Okay. Here directly we are simplifying that, okay. And also we know that it is given the short circuit MEA of the circuit breaker is 333 MVA, okay, means MEA short circuit will become 333. So substitute this 333 value, you will get X is equal to 2.4 per unit after doing simplification all these things, okay. Hence this is the value of the inductive reactance. This is nothing but J 2.4. This is nothing but J 2.4 times the value of which is connected between the transformer and the bus which is required to limit the short circuit rupturing capacity of the feeder across the B to limit that 333 MVA. So this is the unique problem we have.